So, here there is a quick recap of our last session. So, in last session we started dipole and we talk about the field created by the dipole, we talk about the potential due to dipole. So, a dipole, if I say place on x axis, so the field created at journal point which is at distance r, and that r vector is making angle theta, this angle is theta. At this particular point we got two components, one along and another perpendicular, right. So, what we did, we resolved dipole moment in two direction, one along r, that was p cos theta, and another perpendicular to that, that was p sin theta. Right. Due to p cos theta we got field in this direction, and due to p sin theta field was in this direction. The resultant of these two came somewhere in this direction. So, that was the direction of net field, right. So, magnitude what we got was Kp r cube, Kp r cube, p dipole moment, r is the distance from center of dipole, under root in bracket 1 plus 3 cos square theta, that was the net field coming at that particular point. And the angle made by field with this position vector, we assume phi, and that tan phi was coming, tan phi was tan theta by 2. So, this is the angle theta, tan theta by 2 was the angle made by field at that particular point, right. And after calculating field at journal point, we calculated potential. So, the expression we got for potential was, potential at that point P is Kp upon r square cos theta, right. So, due to dipole at any journal point, now we have field and we have potential, right. We did some analysis in the last session, what would be the points where field will be maximum and points where potential will be maximum or minimum, right. So, analysis part we have done completely. And then in the last I discussed that when a dipole is placed in uniform field, when a dipole is placed in a uniform field, so this is representing field and say this is representing dipole moment. So, when a dipole is placed in uniform field, the net force it experiences is 0, because of the positive charge force is in this direction along the field QE, and force on negative charge will be opposite to the field, that will be QE, direction I have taken into account. So, if you look at the free body diagram, the net force on dipole will be 0. So, this force will cancel this force and net force on dipole will be 0, provided it is placed in uniform field, right. Non-uniform field today we will discuss. Then after finding force on dipole, we calculated torque, right. So, with respect to this point, this force will offer torque and try to rotate dipole in clockwise sense. Similarly, with respect to this point, this force will try to rotate dipole in same sense. So, torque produced by both will get added, force due to both the charges will get cancelled, but the torques getting added. When we simplified, we got the expression tau is equal to P cross E, that can be written tau is equal to mod P mod E sin theta, right. So, force came 0 and torque was non-zero, right. If I consider this angle theta, then the torque coming on dipole depends on the angle dipole moment makes with the field. So, if dipole moment is placed along the field, then theta will be 0, and in that case it will not experience any torque. As I keep increasing angle and I make angle 90 degree, then sin 90 will be maximum and the torque experienced by dipole will be maximum. So, dipole may or may not experience torque, but dipole won't definitely experience net force. So, net force won't be there, but torque may or may not be there depending on the orientation. If you just release it, then it will try to align itself along the direction of field, right. So, after releasing it, it will try to align itself along the direction of field, because field is trying to rotate it along itself. So, this is what we had in the last session. Now, let us see what we have today. So, if I ask what is the potential energy associated, now you can see that there is potential energy associated due to these two charges, one negative charge, another positive charge. If I ask what is the potential energy associated, this energy associated, the formula is K Q1 Q2, in this case both are same, one is positive, another is negative, with sign I will write, divide by whatever be the separation. If I am taking separation 2L, then I will write 2L. That is the potential energy associated with the two charges interacting in a space. As we are taking the combination of two charges that we are defining as system, then irrespective of the orientation of this dipole, as the separation between them will remain same, the energy associated due to interaction of these two charges will remain same, right. So, when we are talking about the potential energy, if you want to write, you can write additional potential energy, this one. Otherwise, maximum time we will be focusing on change in potential energy. When you write change for this location or this orientation, then when you rotate it for another orientation, this energy associated will remain same, because we are not going to change the separation, right, and charges are fixed. So, when we are writing potential energy, we want to write the potential energy associated with this two charge system with external field. So, potential energy associated in this situation we want to write as the energy between these two charges and the external field present in a space, right. So, that is why when we are talking about the change, this term which is not going to change will get cancelled out. So, we are not writing this. I hope this point is clear. Now, so if I say at this moment this angle is theta 1 and I want to rotate it slowly so that this become theta 2, right. So, this dipole will have new orientation like this, and this angle I am considering theta 2. I want to find out potential energy associated, right. So, we know work done by external is equal to change in potential energy provided there is no change in kinetic energy. So, if we are doing this process slowly, then whatever work we are doing, that will completely go in the form of change in potential energy of the system, right. Now, as this is a situation where we are rotating something, when we were translating something, then For work we are applying formula F dot dr, force dot displacement, but here we are rotating. To calculate work, this allied here and this allied here, change in potential energy is equal to work done by external, and that is nothing but tau d theta, because we are rotating something, right. Translation F dot dr, rotation tau d theta. So how much torque is needed to slowly rotate it? Field is trying to rotate it in this direction, right, and I am trying to rotate it forcefully opposite or against the field, right. So I am producing torque in anti-clockwise sense and field is producing torque in clockwise sense. As I am trying to rotate it in this direction and it is rotating in the same direction, here my torque will be almost equal to the torque produced by field, because there is no change in kinetic energy. Slowly I am doing this, slowly I am rotating it. So without any change in kinetic energy, whatever work I am doing, that will completely go in the form of change in potential energy. So my torque must counterbalance almost the torque produced by field, and torque produced by field, just now we have seen torque produced by field, that is Pe sin theta. So I am substituting this torque, my torque is almost equal to the torque produced by field, and the value of torque we got in the last session, Pe sin theta, right. So this if I can integrate, I will get change in potential energy. So here I am integrating from theta 1 to theta 2. So this will give me change in potential energy. So Pe sin theta, when you integrate, you will get sin theta integration minus cos theta, upper limit theta 2, lower limit theta 1, right, minus sin, upper limit minus lower limit, right, take minus in, you will get this expression Pe cos theta 1 minus cos theta 2, right. So here what we do, we define potential energy when theta is equal to 90 degree, 0. Potential energy when theta 90 degree is taken as reference, and that we define as 0, right. Why for 90 0? Why not for theta is equal to 0 0? So for that you can understand it this way. If you are bringing a positive charge from plus infinity and placing it here, from infinity you are bringing this positive charge and placing it here. Now bring negative charge from infinity and place it here. In this case, whatever positive work you have done, bringing negative charge from infinity to this point, what negative work you have done, they will cancel each other. So total work done for this orientation will come 0. So as for this orientation, total work done comes 0. We take potential energy associated with this particular orientation 0. Obviously when you are placing along the field, then some extra work you must be doing. For example, bring positive charge from infinity and place it here. Some amount of positive work you are doing, right. Now you are bringing negative charge from infinity and you are not placing exactly over this one, you are placing some distance lesser than that, right. So this is negative charge, this one is positive charge. So obviously for this positive, some extra work you are doing as compared to bringing this negative charge to this particular point where length of path is less. In this path length is less, work done will be less as compared to work done here. So you are doing net positive work in this situation. So considering this one as a reference is not a good idea. That is why we are considering for 90 degree or for this orientation potential energy 0, right. So, I hope reference is clear. Now see, if I put this reference in the expression I just got, so say for 90 degree, look at this expression first, potential energy final minus potential energy initial is equal to, this is change in potential energy, finally it is at theta 2, right. So, I am writing cos P cos theta 1 minus cos theta 2, right. Now, what I am saying is, finally when this theta 2 is made 90 degree, when theta 2 is made 90 degree, this quantity is 90 degree, this whole quantity is 0. So, this whole cos will become 0, right, and final potential energy comes 0. So, say we are moving it from some general angle theta. So, theta 1 is theta. So, I substitute theta here, I will get potential energy with minus sign is equal to P cos theta. So, the potential energy can be written minus P cos theta. So, generalized expression for potential energy is P cos theta. That can also be written as, this can be written as P vector dot E vector with minus sign. By cos theta I can write in terms of dot product. So, the potential energy expression is minus P vector dot E vector, right. So, I hope derivation is clear. So, field was producing torque in this direction, and to rotate against field I need to do work. So, to rotate against field I need to do work, whatever work I am doing that will go in the form of change in potential energy, provided there is no change in kinetic energy. So, this logic I use to reach to the potential energy expression. As I already told you that we are not talking about the internal energy associated with the system. So, positive charge and negative charge, this system will form some internal energy which is given by K Q1 Q2 divided by R, right, because that is not going to change. So, that is not going to change. So, when you are writing change, that will common term will get cancelled out. So, this is the energy associated with the external field and the dipole. So, for this combination we have calculated potential energy associated, right. So, I will erase all. So, what we have got, we have here potential energy associated is minus P vector dot E vector after simplification. This is the result. Now, look at the result. In a scalar format it can be written this way, mod P mod E, whatever be the angle coming, right. So as I already told you, when theta is equal to 90 degree, then potential energy associated when theta is equal to 90 degree, that is 0, right. When it will have the maximum potential energy, look at this function, right. Here cos is written, but in front we have a negative sign. So when cos will become -1, this minus and this minus will make it plus. So the potential energy will be maximum, when theta is equal to 180 degree, right. When theta is equal to 180 degree, this cos 180 minus 1 minus minus will make it positive, then you are going to get this, right. And when is the potential energy minimum? When cos, this quantity will become +1, then with +1 minus, if you multiply, then this will become minus, right. So potential energy will be minimum when theta is equal to 0 degree and the value will come minus P vector mod E vector, right. So this is for 90 degree, this is for 180 degree, and this is for theta is equal to 0 degree, right, minus P. Now this position, that potential energy maximum is unstable equilibrium, and this is called stable equilibrium, right. So this is called stable equilibrium, and this one is unstable equilibrium. What's the meaning of stable and unstable equilibrium? Let's see that. So now I'll erase this one. If I place dipole this way, when positive charge is here and negative charge is here, I am placing dipole this way, right. This is the way I am placing dipole. If I slightly displace it, then this positive charge will come here and this negative charge will come here. When I rotate it by an angle theta, I slightly displace, then what happens? Field exert force on this positive charge in this direction QE, and on this negative charge it will be QE in this direction, right. As you can see that field is trying to bring the dipole back towards its initial orientation, because this force will offer torque about this point, that torque is coming in inward direction, and this is also offering torque about this point in inward direction, R cross F. R cross F, thumb is coming in inward direction. I am using right hand rule to calculate torque. Tau is equal to R cross F formula, basic formula for torque. Similarly for this one, if I see, this is R, this is with respect to this point, this is R cross F, again thumb is coming in inward direction, both are coming in inward direction. Inward direction means clockwise sense, right. So forces coming or appearing on the charges due to field, they are trying to rotate the dipole in the opposite sense what we have rotated it. So it has got tendency to get back to the initial position. That is why for this one, this theta is equal to 0 is called stable equilibrium, right. So theta is equal to 0 is the stable equilibrium because it is having tendency to get back to the initial position, and why equilibrium? Because net force is always 0. Now instead of placing it this way, if I place dipole this way, instead of placing it this way, now I place the dipole this way. Look at the diagram. Now I am placing positive charge here and negative charge here. If I slightly rotate it, if the dipole is slightly rotated, now this positive charge will come here and this negative charge will appear here. If you look at the torque at this moment, force acting on plus q charge is in this direction, that is QE, and force acting on this negative charge is QE in this direction, right. You have rotated it clockwise and the torque coming due to field is also in the same direction. Again R cross F you can check, R cross F, this force will try to rotate in clockwise itself and this one clockwise. So both are trying to rotate in clockwise and you have also rotated in clockwise. So you disturb the equilibrium, you rotated it slightly, when you release it, it will become like this. So from this location, as you slightly rotate it and release, then it will become like this. So it has no tendency to get back to its initial position. That is why it is called unstable equilibrium. So unstable equilibrium meaning is clear, stable equilibrium meaning is clear. Stable equilibrium, when I am placing dipole this way, I rotate it slightly, release it, it will try to get back to the initial position. It has got tendency to reorient itself. But when it is placed this way, with the field this is making 180 degree, with the field it is making 180 degree, at this moment it has got the maximum potential energy and you slightly disturb it, then it will completely rotate and try to align itself along the direction of field. That is why that is unstable equilibrium. So stable equilibrium, unstable equilibrium. So expression of potential energy, expression of torque, what is a stable equilibrium, what is unstable equilibrium, all these points are clear. Now let us see few example based on the dipole so that you will be having better understanding. So I have taken a very simple example, like dipole moment is given by 8I plus 6J and it is placed along x axis, right. You need to find out the field due to dipole at distance r from dipole on x axis and y axis, and you need to locate the point where the potential energy associated is maximum and minimum, right. So there are basically two parts of the problem, one is something related to field and another something related to potential, both the expression we know, right. So let us place the dipole. So 8I plus 6J, that means dipole moment magnitude is what? If I just write the magnitude of dipole moment, that is under root 8 square plus 6 square, this will give me 10, right. And in space it will be something like this. This 10 will be this way. So x component is 8, y component is 6, y component is 6, x component is 8. So angle it makes with x axis, say tan theta, that is y component divided by x component. 6 by 8 means 3 by 4, 10 3 by 4, 37 degree. So, here it will be 37 degree. So, this is the way dipole is placed in a space, right. Let us first see second part. So, I want to locate the point of maximum and minimum potential, right. So, from here I will draw circle of radius r, right. So, some small distance r, circle I will draw. Now, this particular point, this is on the axis of dipole, and our formula was with respect to center of dipole. If I draw line and join to the point where I am interested in calculating potential and field, what angle that line makes with the direction of dipole moment K P cos theta divided by r cube. So, the potential will achieve its maxima when this quantity is 1, and potential will achieve its minima when this quantity is minus 1. This is r square, not r cube. So, after getting the resultant of this dipole moment, I will be having idea about the axis of dipole. Potential at this point is maximum, and the value of that will be Kp divided by r square, and potential at this point will be minimum, and the value of potential will be minus Kp divided by r square, right. Perpendicular to this one, perpendicular to the dipole moment, somewhere here and here, with respect to dipole, this angle, look at this angle. If this angle is 90, then potential will be 0. So, potential will be 0, potential becomes 0 when theta is equal to 90 degree. So, this and this point here and here, potential 0 and potential 0, right. If I ask what is the field at this particular point, what is the field at this particular point? On the axis, direction of field will be like this, and the value, formula was formula for field. So, I will erase this and there I will write the expression for field. So, maximum minimum potential location clear. Now, we talk about the field. With respect to dipole moment, if r vector is making angle theta, then formula came Kp r cube under root 3 cos square theta plus 1. This was the formula we derived for field. Now, with respect to dipole, with respect to dipole moment is in this direction. So with respect to dipole moment at theta is equal to 0 in the same direction. If I want to find out, here I write theta is equal to 0. So this will be 0, cos 0 1, this will become under root 4, that will become 2. So here field will be 2 kp divided by r cube. Same will be the direction of field and magnitude of field at this particular point. So at this particular point field will be in the same direction, and that is 2 kp divided by r cube. And perpendicular to the dipole moment is the bisector. For bisector, this will become theta. From dipole moment, this angle is theta, right. So when theta become 90, this will become 0, and this will be kp upon r cube, and we know that it will be opposite to the direction of dipole moment. So dipole moment direction is like this, field direction will be opposite to that, and the magnitude of field will be kp divided by r cube. Here this is 2 kp, right, because along the axis or on the axis, on bisector it was kp divided by r cube, and whatever be the direction here, same will be direction here, right. So this way I can talk about any point in a space. For example, if I ask what would be the potential and field at this particular point, what would be the potential and field at that particular point. So field formula is this, and potential formula is kp divided by r square cos theta Now I want to find out potential and field at this particular point. I will erase all this. So at some general point you are asked to find out field and potential. Now with respect to this one, r vector will make this total angle is 90, this remaining angle will be 53, 90 minus 37, right. So that angle will be 53, and this is nothing but theta, right. Theta is equal to 53 degree. So to get what is happening here, this is r vector, this will be r vector, look at this. Now this will become r vector, and from dipole moment it is making angle 53. So I need to just set this angle 53 to get the magnitude of field, and to get potential I need to set this angle as 53. So just substituting the angle, you will get corresponding value of potential and field at this particular point. So now we have got E and we have got V. So this analysis is clear. We calculated second part first. Now let us do first part. On x axis, now question is on x axis what is the field on x axis. So from dipole moment you can see this angle is 53, y axis I have already done, for y axis this is 53, right, and for x axis with a dipole moment it is making minus 37. So I can set for this point, I can set here angle 37, right. So directly in the expression I will substitute the value of theta, I will get the magnitude of field. But if you want to write in vector form, So, let us see this, because this is just giving you magnitude, right, and you have to apply formula of tan phi is equal to tan theta by 2 to get the direction at that point, or else we can do one thing. Now, I am giving you another method of doing it, right. So, I will erase all what is not required. So, let us get back to first part of the problem. Now, what I will do, I am telling method to you. So, method 2, instead of applying these two formula, I will directly write field in vector form. As you can see that I can assume there are two dipoles, one is placed along x axis, another dipole is placed along y axis. So, we have got one dipole of dipole moment 8 here, and we got another dipole moment 6. I can break it this way. So, one dipole of dipole moment 6, another dipole of dipole moment 8 is placed like this, right. And now I am asking what is the field at x axis. So, somewhere here, what is the field? See, because of this 8, look at 8, because of this dipole, this point is axial point, and for axial we got formula 2 kp divided by r cube. So, if this distance is r, then we got x component of field as 2 kp divided by r cube along the direction of field, and formula was 2 kp divided by r cube, where p is 8. So, in place of p I will write 8. Now, look at this 6. Because of this 6, as this point is bisector on bisector, field will be opposite to the dipole moment, and the formula is kp divided by r cube. So, in this direction there will be field, and that will be kp, in this case 6 divided by r cube. So, if you ask what is field at that particular point, then I can write 2k8 divided by r cube I cap, because this is along x axis. As this is along negative y direction, then I can write k6 divided by r cube j cap. So, now we got field in vector form. Same thing I can do for this point. for 8 it is bisector. As it is bisector for 8, this I can write K8 divided by R cube. For 6 it is axial. What I can write? 2K8 divided by R cube. So field on y axis I can write minus K8 divided by R cube I cap plus this I have written here. Now I am going to write this one. So that is 2K8 divided by R cube J cap. Let's call it 0.1, right. So this is 0.1 and this is 0.2. So field at 0.2, field at 0.2 is in vector form this way and field at 0.1 in vector form this way. So easiest thing you can do, you can resolve the component and find out the field. Let us take one more example, then it will be more clear. Now instead of saying that there is a single dipole kept in a space and it is given in vector form 6i plus 8j or 8i plus 6j, if I say there are two dipole placed, so now we have got two dipoles in a space. So this is one dipole, let us say its dipole moment is √3 times p, and there is another dipole which is placed like this. Let us call it P1 and this is P2, P2 is P, right. So I am drawing it with different colors so that you can understand there are two dipole placed, one along x axis, another along y axis, and at general point if I ask what is the dipole moment, for example now if I ask what is the dipole moment here, then because of this dipole you can write the field at this particular point, and because of this dipole at that particular point it will be 2, because of blue one I am drawing the field. So let us take blue one first. So because of this one at this particular point field will be in this direction and the magnitude is Kp divided by R cube, 2 times axial. Now because of this one field will be in downward direction opposite to this, and the magnitude is K, because this is axial one, then K instead of P, because its dipole moment is 3p, I will add 3p divided by R cube. Adding these two will give me resultant. Same thing I can do for this particular point. Because of this one field here will be Kp divided by R cube, direction opposite to the dipole moment, and because of the red one it will be in this direction and the value will be 2k times √3p divided by R cube. Writing them in vector form, ij form, I will get the field in a space in vector form. Or for example if I say from here at an angle 60 degree, what is the field? or from here at an angle 30 degree, what would be the field? So this first one is clear. Now at any general angle I want to find out what is the magnitude of field at that particular point. So we can draw the resultant of these two. What is the net dipole moment? Because dipole moment is a vector quantity itself, so what I can write, the net dipole moment of the system, of these two dipole system, is first one vectorial added with the second one, vector addition. The angle is 90 degree, I can directly write a square plus b square under root. So a square plus b square under root, so net dipole moment is p square plus root 3p whole square under root, and this will become what? 2p. So these two can be replaced by a single dipole, these two can be replaced by a single dipole having dipole moment 2p and angle made y divided by x, angle it makes with x axis. So tan say theta, the angle with x axis is root 3p divided by p, this theta is coming 60 degree, right. That means these two can be replaced by single dipole having magnitude p and making angle 60. Now these two are not needed, this red one and this blue one not needed. I have converted these two dipole system into one dipole, right. So from here if I ask what is the field at this particular point. So the formula we have for the net field, that E is equal to Kp divided by R cube under root 3 cos square theta plus 1. I need to just plug in 30 degree here. So just put 30 degree here, because from dipole if this angle is total is 60, this is 30, I need angle, this theta angle is from dipole moment. So dipole moment is in this direction, and from dipole moment this angle is 30 degree. As this is in this direction, we will write minus 30, it won't make any difference because it is square, right. So here I will substitute just 30 degree, I will get the field at this particular point. So when multiple dipoles are given, you can combine them and make one, and with that one you can easily apply this formula and get the field at any given general point, right. So whole concept of field and potential is clear. Now let us see one more example. Find the torque experienced by a ring placed in uniform field. E is equal to 3I minus 4J, right, and charge is linearly distributed over ring. So charge is linearly distributed over ring and it is given by lambda is equal to lambda naught cos theta. So cos function, look at the cos function, first quadrant it is positive, second and third quadrant negative, and fourth quadrant again positive, right. So here this angle is, this angle 90 degree, this angle 180 degree, right, this is 270 and this is again 360. So first quadrant cos is positive, this is cos theta and this is theta, right. So first quadrant cos is positive, second quadrant negative, then third quadrant again negative, fourth quadrant positive. So if I start distributing charge, then according to this function cos 0 will be highest, then here density will be highest, and as you keep moving the density reduces, right, and somewhere here it will be almost 0. At theta is equal to 90 degree, the density here will become 0. As you cross 90 degree, it starts becoming negative and minus sign, charge with minus sign start appearing, right, and as the angle start becoming 180 degree, the density of charge will be more because cos 180 degree is minus, right. So here density will be more, right. So first quadrant over, now first quadrant over 90 degree over, another 90 degree we have covered. So we have reached up to this point, and from here onwards again it will be negative, but the density keep reducing. So here it will be negative, but the density keep reducing. So you can see the gap here I am drawing and gap here I am drawing is different because it is non-uniformly distributed. When I cross 270 degree, then again it starts becoming positive, and this side plus. So distribution will be something like this, right, you can visualize it easily. Now I can replace this whole thing by a single dipole, and after getting dipole moment I can easily calculate torque using P cross E. So instead of writing force on each and every element and then calculating torque with respect to center and integrating, I can convert this one into single dipole, and single dipole placed in electric field, how much torque it experiences, we know the expression, we can directly get the result. So I hope approach is clear. Let us see how to apply that. So I will just somehow convert this into dipole, right, and you can see whatever be the charge here at an angle theta, which is subtending angle d theta, same will be the charge this side at an angle theta and subtending angle d theta. Cos 180 plus theta and cos theta, right, same value. So here this will play the role of negative charge of dipole, and this part will play the role of positive charge of dipole, and this combination will behave as dipole, right. So I can combine these charges which is in first quadrant to those charges which are in third quadrant and make dipole. Similarly I can see these can be combined with these charges and it will form dipole. So this is one way of looking into the system. There is one more way of seeing the system. So first see this one. So here from negative to positive, this is dp. If I take element somewhere here, then dp will be something like this, dp. If I take this and this, then dp will be like this. Then I start combining this with these, then dp will be like this. So this is first way of thinking that these are the dp and we need to add dp to get the total dipole moment of the system, right. In this case what is happening, that vector is changing its direction. So I can resolve the component. If I am writing it this way, then for general angle theta I will write dp cos theta. Dp cos theta will give me x component of dipole moment, and dp sin theta will give me y component of dipole moment. You can see dp cos and dp sin. Add them separately, you can easily see their y component will get cancel out, these y component will get cancel out and x component will get added. So net dipole moment you will get in x direction, y will automatically come 0 once you integrate it, only x will be there, right. So this is one way of seeing it. There is another way of seeing it. another way of seeing it. Instead of combining this negative charge with this negative charge with this positive charge, I can take charge somewhere here. What I am saying is, instead of taking this minus dq with this positive dq, I can take somewhere here where this is subtending angle d theta. I can combine this dq with this dq, and you can see that this minus dq and this plus dq, they are also forming dipole. So the same system can also be visualized as this dp, this dp, this dp, take negative here, positive here, this dp, this dp, this dp, this dp. So I can also visualize as dp, 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 dp like this. So all dp's are in same direction, I just need to add. Whether you go by this procedure, or you go by this procedure, you are going to get the same result. You can check that, right. So say this is method 1 and this is method 2. Any method you solve the problem, you are going to get the same result, right. It depends on you what suits you. So let us take one of the method. So say we are going by this method. So all dp's are in same direction, right. So I will combine them in such a way so that all dp's are coming in same direction. So we are going by method 2. Look at this, dp is, what is dp? Charge into separation. So charge is dq into separation. Separation is, this distance is r, then this distance will be r cos theta towards angle r cos theta. So this distance is r cos theta. Same thing happens here, this is r, so this distance will be r cos theta, this distance will be r cos theta. So total distance will become 2r cos theta. So here I will write 2r cos theta. Now dq, linear charge density is given, lambda is equal to lambda naught cos theta, and we know linear charge density is equal to dq divided by length. Length of the element is, if this is r, this is d theta, length of this element will be r d theta. I will write r d theta here. So from here I can write dq is equal to lambda r d theta. From here I can write dq is equal to lambda r d theta. So substitute lambda r d theta here, lambda r d theta into 2r cos theta. And what is lambda? Lambda is equal to lambda naught cos theta, it is a variable. So I will substitute the function here, lambda naught cos theta into r d theta into 2r cos theta. This dp we are getting in what direction? All these dp's, all such dp's will be in same direction. So this what we are getting, that is in x direction. Now we need to just integrate to get the answer. Limit. So generally student commit mistake in putting the limit in all such situation. So you can see, once you are taking the element somewhere here, you are combining this element with this element, that means at the same moment you are covering, when you are going from theta is equal to 0 to 90 degree, you are covering this part as well as this part. So from theta is equal to 0 to 90, you have covered this part as well as this part, because this you combined with this one, right. Look at the lower part. When you put angle from 0 to 90 minus 90 degree, because you are going in opposite direction. Earlier you are going in anti-clockwise direction, now you are going in clockwise direction. So when you go like this, then you are combining this part with this part. So if you substitute limit from minus pi by 2 to plus pi by 2, minus pi by 2 to plus pi by 2, you have already covered this part, right. So limit will be from minus pi by 2 to pi by 2. So lambda naught into r square, 2 I will take out, 2 is outside, and then I am getting cos square d theta, right. This will make it cos square. Cos square theta, that we can break into linear function, and then I can integrate. So I know that cos 2 theta is 2 cos square theta minus 1. So when I get this from this side, then I will get cos square theta as cos 2 theta plus 1 by 2, that I can write here. So look at this one, 2 lambda naught r square cos square theta, I will substitute that here. So there are two parts, cos 2 theta by 2 and 1 by 2, separately I will write, right, I am directly writing it. So cos 2 theta d theta by 2 integration minus here plus d theta by 2 integration limit minus pi by 2 to plus pi by 2, minus pi by 2 to plus pi by 2. Now you can see that integration of cos 2 theta is sin 2 theta, upper limit minus lower limit. So if I write sin 2 theta here, sin 2 theta and minus pi by 2 to plus pi by 2, if I do, then look at this one, in place of theta if I substitute pi by 2, then 2 will get cancelled out and you will get sin pi, which is 0. Then you will put the lower limit, then again minus pi is coming, again it is 0, that means this whole integration will be 0 only. And this one d theta integration will be theta upper limit minus lower limit, pi by 2 minus pi by 2 will give you pi, then this 2 will come and that 2 and this 2 will get cancelled out. So what I can see is lambda naught r square and the pi what we are getting here. You can simplify on your own and you can cross verify it. So this is the dipole moment we are getting finally after simplifying it. You can also cross check by method 2, right. So now let us get back to what is the question. Question is torque. We need to find out torque. Torque it experiences when it is placed in uniform field, which is given by 3I minus 4j. So first part is over, we calculated dipole moment. Using that dipole moment I can calculate torque. So I will erase all this which is not required. that means this whole distribution can be replaced by a single dipole. What we got? Dipole moment we got lambda naught r square pi. And what was the direction? All dp's were coming in same direction. So in vector form I can write this way, right? So this whole thing I can replace, by single dipole like this, and which is placed in field given by 3i minus 4j, right? 3i minus 4j will be like this. It will have I positive and j negative, right? So this is the way it is kept. As it is not along the field, obviously it will experience torque. The expression for torque is tau is equal to p vector cross E vector. Now p you can substitute from here, lambda naught r square pi I cap and cross 3i minus 4j. If you simplify, then you will get lambda naught r square pi I cross I 0, I cross I both are in same direction. Formula is I cross I is mod I cos, angle between them is 0, sorry, cross product we are doing, right? Angle between them is 0, right? So cross product formula A cross B sin theta, right? So here this angle is 0, this value will be 0. Now next one will be I cross J. I cross J is K, right? So I am directly writing I cross J is K. So you will get minus K over here. So 4 outside, I will take this 4 outside and I will write minus K cap. So this is the torque experience. Minus K means inward direction. So that means if you release the whole ring, it will try to rotate, minus K is coming. So put thumb in inward direction and finger will give you the sense of rotation. So finger is giving me clockwise direction. So if you release this ring in this field, it will try to rotate in clockwise direction. If I give you moment of inertia, I can also ask initial angular acceleration. So if I say mass of ring is m and the radius of ring is r. So second part if I add on this one, second part, find initial angular acceleration of ring. Initial angular acceleration of ring, right? So I can write torque I got. So tau is equal to I alpha, right? Substitute the value of torque here, that is 4 lambda naught r square pi is equal to moment of inertia of ring. It will rotate about this axis. So about this axis moment of inertia of ring is mr square. So here I can write mr square alpha, right? So from here you can get alpha is equal to 4 lambda naught r square pi divided by mr square. So using the concept I can find out the torque, right? And from torque I can give answer of the remaining questions. Now, so this is all about what we have for x direction, right? When field is uniform, then how to find out torque, how to find out force. Now what if the field become non-uniform, right? So non-uniform force and torque, how to find out? Let's see. Let's first talk about the force. So if dipole is placed in 3 dimension, I am writing everything. So say we have got dipole in this direction, P in this direction, vector form, and we have got field in this direction, both are given in vector form. So dipole moment vector form, we have just seen one example. This can be written pxi, these all are suffix, right. So pxi, pyj, pzk vector form it is written. Similarly field is written in vector form. Now I want to find out force. So what we can do, we know that force can be easily calculated with the energy, right. So F is equal to minus du by dr. So if I have energy, I will differentiate with respect to r, then I will get force. If this r is given in vector form, I can do this one, del by del x I j k. So if I get the potential energy, I will differentiate potential energy partially with respect to x, with respect to y, with respect to z, I will get k, right. So with potential energy I can easily reach to the force, and we know that potential energy is given by p vector dot e vector. So if you do dot product here, minus p dot d, so I dot I 1, j dot j 1, k dot k 1. So this will come in this form, this will get multiplied with this one, this will get multiplied with this one, same way. Now you have u, right, and we know that F is equal to del operator u. So in simplified way, if I want to write, it can be written this way. Just now I wrote right, this is del operator into u. So you need not to worry about what the del operator is. For time being you can remember in this way, right, partial derivative with respect to x I cap. So I will get u inside, right, and u I already have, so I will place it here and simplify. So look at this one, all these term, all those whole term will appear with x, will appear with y, will appear with z, whole expression will appear with x. So I will get partial derivative of this, this and this with respect to x, right. Let us see the expression first. So if field is non-uniform, field will be changing with x. So the whole expression partial derivative with respect to x. So this x partial derivation with respect to x. Then next term, see this term here. So this partial differentiation with respect to x. Then this partial differentiation with respect to x only, right, this will come. This whole thing will give me I cap, right, and then the whole thing with respect to y. So the whole thing with respect to y, this with respect to y, this with respect to y, this with respect to y. It looks lengthy when you write in vector form, everything will get simplified and you will easily get the answer. Similarly, all these will appear here, and x with respect to z, y with respect to z, and z with respect to z. All these terms you will get, and this way you can easily get the force, right. So today I was unable to start our next topic, Gauss law. So next class we will be starting Gauss law after doing some solved example on this particular topic. So I hope you understood today's concept. So keep practicing, assignment is already uploaded, right.